We're in chapter 4 now. Let's go over our first example for chapter 4. Remember, we're dealing with mass flowing in and out of our systems now, so we've added a little bit of complexity. In this example, we've got air. It exits a turbine at 200 kilopascal, that's our pressure, and a temperature of 150 degrees Celsius with a volumetric flow rate of 7,000 liters per second. We're going to be modeling our air as an ideal gas, and we want to determine the mass flow rate in units of kilograms per second. Now, before we get started, let's make sure we look for any sort of keywords. First of all, we've got air. It's always good to know your substance. We've got our pressure. We've got our temperature. And notice this says volumetric flow rate. That's 7,000 liters per second. And we've got an ideal gas. Definitely want to pay attention to the ideal gas part. Now we've underlined all of that. Let's go ahead and write out the values we know. So P, we don't really need a P1. Pressure is going to be 200 kilopascal. Temperature is 150 degrees Celsius. Volumetric flow rate, do you remember what symbols we had for that? Is A times V, area times velocity. And that's going to be 7,000 liters per second. We also know that this is an ideal gas. Let's write down that ideal gas equation so we know we can use it. So PV equals RT. And we're looking for mass flow rate. Mass flow rate is m dot. Let's go ahead and write down the equation for m dot because we know we need to find that term. And I chose to use this one because I've already got a V here. So this one will be easy to use. Okay, so now we've got that. We need to have specific volume though in order to find m dot. Notice that is found in here in the ideal gas equation. So let's start with this one. We'll find specific volume using the ideal gas equation. So V is going to be RT over P. And remember, R is R bar over molecular weight. Multiply that by temperature, put that over pressure. Let's plug in our values. R bar that we need is 8.314. That's just that constant number we wrote down a long time ago. Molecular weight for air is going to be 28.97. That comes from the table. And the units, if we write all the units out for this top one, we're going to have kilojoules per kilomole Kelvin. Underneath that, for the molecular weight, we have kilogram per kilomole. So looking at that, you can see we get rid of the moles. So that's good. We end up with kilojoules per kilogram Kelvin. Now, after that, we need temperature. So let's do our temperature. Our temperature is 150 degrees Celsius. Can I just write that in there and be done? Nope, you're right. We can't do that. We got to have 273 added to that. That'll take it to kelvins, which is what we want because we need that absolute temperature scale. Then we're going to divide by pressure, which is 200 kilopascals. And I'm going to be out of room here. This is going to be kind of annoying. Now we've got this in the denominator. Now kelvins is gone. Now we're left with kilojoules per kilogram over kilopascal. That is not what we want for units of specific volume. So we need to do some conversions here. And it's going to be annoying because I ran out of room here. I thought I had enough room, but I write too big. So let's go down here and let's put an arrow. We're going to multiply this by these conversions. So we got the 1,000 Newton meters per kilojoule. And then that gets rid of the kilojoule part. Then we're going to have the conversion 1 kilopascal per 1,000 newtons per square meter. Okay. Now after you multiply everything together, you get rid of your kilopascals, everything works out, and you'll get V equals 0.607 cubic meters per kilogram. So that's going to be V. Now this is what we needed for our m dot equation. So let's put a line under it. Now let's go to this equation and finish the problem. So we'll just come over here. Our volumetric flow rate was given as 7,000 liters per second. We obviously don't want to leave things in liters, so we need to convert. And the conversion, we want to go to cubic meters. So there are 10 to the negative 3, it shouldn't be an L, cubic meters per liter. That's the conversion we need, and then we're going to divide that by specific volume, so 0.607 cubic meters per kilogram. Notice the liters go away and the cubic meters go away. So now you're going to be left with units of kilograms per second, which is what we want for mass flow. So that is a good sign. So now if you do the numbers, you get 11.532 kilograms per second. That's an S, not a 5. And that is m dot. So this is your mass flow rate. You've got 11.532 kilograms of air entering your turbine or exiting your turbine per second. That's what this number tells you. Okay, hopefully you like that example, and I will see you in the next video for the next one.